Hi there, my name is Kevin Stuart. I am a research scientist at Hubbs-SeaWorld Research Institute. I've been with the Institute since 2003. I did my undergraduate work at University of Delaware, majored in biology, minored in chemistry. Did my graduate work at Clemson University with a master's degree in aquaculture, fisheries, and wildlife. So I'm going to talk to you today about a little bit what I do. My main responsibilities are overseeing the research down at our Mission Bay laboratory, research that encompasses everything from our adult fish to our juvenile fish to our eggs and larvae. And so that can range in anything from genetic work to nutrition work to general husbandry. We work on three main species here. White sea bass, which is our main stock enhancement species, California yellowtail, which is a species we are looking at as food production, and California halibut, which is the up-and-comer for our stock enhancement program. So today, I guess I'll talk about a little bit of the research that we are doing with our California yellowtail. We've been working with California yellowtail since 2003, so we have an extensive amount of experience on it. My main focus over the years has been the larval phase, so both for larval culture, larval nutrition, figuring out the best environments to raise them in, be able to increase both the quality of the larvae as well as the quantity of the larvae. And so some of those trials end up looking as, we try to do everything as a replicated trial, a replicated study, trying to do the best science practices that we can. And we have multiple systems that we can run these larvae in. We'll raise them from egg to 18 days post-hatch, or from all the way up to a juvenile stage. We've looked at anything from the light levels that we add into the tank to the type of food that we're offering. At the Institute here, we do grow our own live prey, so we grow rotifers and artemia. A rotifer is a form of zooplankton. It is, over the years, the best way that I've always had a rotifer described to me is that it's an envelope. If you think of it as an empty envelope, you want to put everything that you can into that envelope to get to the larvae. In the wild, the larvae will eat natural zooplankton, copepods mainly, and what we try to do is mimic that nutritional profile of a copepod into a rotifer. So we try to put everything we can, enrichment-wise, into the rotifer to get to the larvae, so that we can minimize any type of malformations and increase growth and survival.
What type of items are you talking about that go into the rotifer? You said it's an envelope. What goes into the envelope?
We're looking at basically essential fatty acids, and a lot of those come from emulsions that are commercially available. And we also do things with our collaborators. We collaborate over the years. We've collaborated closely with Oregon State University to really hone in on specific values for those essential nutrients. So things as taurine, or right now we're working on vitamin C, trying to really optimize and customize these enrichments for the species that we're rearing.
So how big? So these larvae are how big, and how big is the rotifer to them? Like, it's just a little prey item kind of thing. I'm trying to picture it.
Yeah, the rotifer, depending on the type, can be between 150 to 300 microns. I wish I had a scale for you to see, but under a microscope, you can see them with the naked eye.
Is it like us eating a Twinkie?
It's like us eating a nerd.
Okay.
Maybe a little bit smaller. Basically, what you're trying to do with larval rearing is you're trying to put the biggest prey item that they can fit in their mouth, because they're always looking for the next biggest prey item. And so when their mouths open, it's only probably the mouth opening is probably only like for the yellowtail 300 to 400 microns. So they could probably only fit the rotifer at that point. As they grow, they're looking for a bigger prey item. So that's why we transitioned to second instar Artemia. And the only reason we go, and Artemia is a sea monkey. And initially when you hatch the Artemia, the first instar Artemia they have no eye spots, they have no mouth, you can't enrich them. So we've skipped that phase and go to the second instar, which you're able to enrich. And we try to put the same enrichment or similar enrichment for the rotifer into the Artemia, depending on the life stage. And now when you start getting into the different species, the different life stages need, as they grow, they need different requirements. So we have to section the life stages into, we have to section the life stages, so we have to, the same enrichment might not happen for the rotifers as it do for the Artemia. And so as you keep getting bigger and bigger, you try to transition them to larger prey items. And then once the whole end game is to get them off the live prey, because live prey are not as reliable as a formulated feed. We want to increase biosecurity and all that stuff to a formulated diet, which you're basically training them to go after an inert particle. And there's a whole science behind it where you're trying to put in attractants that leach from the particle to get the larvae to smell it and to notice it. You try to get a certain sinking rate to mimic what the live prey would be, and as soon as they start learning to eat that prey item, you remove the live prey, and then you can end up adding bigger and bigger particles till you get to a formulated, like a commercial diet.
So it's like a transition time.
Yep, and so you do the same thing with your rotifers and Artemia. They're not naturally looking for the swimming movements of a rotifer. They're genetically trained to look for the swimming movements of a copepod. So they have to learn that this is the food item. So there's a lot of, if you look in a larval tank, there's a lot of swings and misses. So you'll see the larvae kind of get into an S position and then strike, but sometimes they won't hit it. So in that respect, you try to either help through light intensity, or we use algae paste as a contrast to help them find that prey item. And so they can get more successful strikes, and as they get more successful strikes, they eat and they develop, and those good things start to happen. We have fine-tuned the larval rearing phase so that I feel like we are very successful. We have successful in survival as well as growth. We can produce from egg or recently hatched larvae to a 50-day fish. We can get 30 to 40% survival, which in the aquaculture world is pretty successful.
So we have many fish in our care that require not daily feeding, but routine feeding. What has this quarantine, the COVID-19 quarantine, done to affect the work that you're doing with your team in keeping these fish fed, healthy, and to continue these type of studies you're doing?
So we pretty much pushed a pause button, put a pause on our live prey culture, just so that we can focus on. Every population is important, but in order for us to do the research that we do, and specifically larval rearing, we need the adult populations, because if we don't have the adult populations, we don't have the eggs, and then we can't continue our research. The adult populations are getting all of our attention. We're doing our best with social distancing, but the broodstock are continuing to get fed, being cared at our best to our best ability. Right now we're getting spawns every 2 to 3 days from our California yellowtail, every other day from our halibut. They seem happy and healthy, and once we're unpaused, we'll be ready to hit the ground running.
So where's your family, Kevin? Are they here in the west or out east?
I have my older sister's in Encinitas. She has 4 kids. She's probably going crazy. My parents are in Illinois. and my two brothers, my older brother's in New Jersey, and my younger brother's Long Island.
Everybody healthy?
Everyone's healthy.
Good.
Everyone's happy.
Good. Thanks for your time, Kevin.
Thank you.